Okay, let's get started. Morning, everybody. Welcome to the UK Pharmacogenetics Stratified Medicine workshop on polygenic risk scores. This is a really important area, and we've got 80 people who registered for the sort of meeting today, and we've got 60 already online, and I'm sure others will be joining. We've been through a hell of a year, I guess, and all of us have had to deal with issues in our different ways, either professionally or personally. We did hold an annual meeting last year at the Royal College of Physicians. It was just before lockdown, the week before lockdown. And then we decided not to hold any meetings last year because of all the different pressures different people had. But we decided to start again. So this is the first time that we're holding a virtual workshop. And there's obviously some positives to that, but also some negatives. The positives are that we get many more people registered. As I said, we've got 80 people registered. The negatives are that we don't have that social interaction that we can have when we meet for coffee and so on at the meeting. But we've got some fantastic lineup of speakers who are going to take us through this. And this is a really important area, still in development, but real opportunities in terms of taking this further forward for academia, for healthcare, as well as for industry. So and this may be the first of a couple of workshops that maybe we do in this area, because there's a lot to discuss in this area. So just some housekeeping points. I think for when the speakers are on, it'd be great that if you switch off your cameras, so that, and just in case anybody has any difficulties with bandwidth and so on, because I think some people can have problems with bandwidth, and obviously switching off cameras helps in terms of reduction of bandwidth. The other is in terms of, if you've got questions, please put them in the chat. And I will be there will be time for questions at the end of each talk. And what I will do is I will sort of read out your questions to the speaker, who can then answer the questions. I'm going to sort of chair the first part of the meeting. I have to drop off at 1 o'clock, unfortunately, so apologies. I have to go and do an urgent COVID-related meeting at 1 o'clock. And Professor Ewan Pearson, from Professor in Dundee University, is going to take over from me at 1 o'clock, and he will also then chair the post-lunch session where you have the breakout rooms as well as the feedback from the breakouts. Nathan has been working hard to be able to set this up. So Nathan, thank you very much. If I don't get a chance to thank you later on. And Nathan is also recording as well. And as we normally do, we will put this up onto our website. For those speakers who have agreed to have their talks recorded, we will put that up on our website to reach a wider audience for wider dissemination and so on. Okay, so thank you very much for that. So that's my initial comments. So a great pleasure to start off the symposium workshop by introducing Professor Valentina Escott-Price. Thank you very much for agreeing to do this talk. Valentina is a professor at Cardiff University, works with the Dementia Research Institute, and has a background in big data, is part of the MR Centre for neuropsychiatric genetics in Cardiff, as well as having responsibilities for postgraduate research as well in Cardiff as well. So Valentina, we very much look forward to your talk. Thank you very much for doing this.
Hello everyone. I'll start sharing my screen. Okay, so my name is Valentina Escott-Price, and as it was introduced, I work in the Dementia Research Institute and also in the Center for Neuropsychiatric Genetics and Genomics at Cardiff University. Just to tell you about myself a little bit, I'm a mathematician by background, so not a biologist, not a clinician, so please ask me technical questions accordingly. And also you will see the reflection of my background in my talk, because it will be mostly numbers based, or even sometime I put one formula in. just to know what we are talking about. Okay, I'll be talking about Alzheimer's disease because lately, last 6-7 years, I mostly work for Alzheimer's disease. And polygenic risk score I'll introduce in details in a second. However, let's start with the heritability. So why we are looking at polygenic risk scores? Because obviously we know that Alzheimer's disease is heritable. And if you look, that is a picture from our recent review. So genetics broad sense heritability, which means coming from twin studies, accounts between 60 and 79%, which is quite high, which makes sense to study genetics of Alzheimer's disease. Also, we know that about 35% of risk to Alzheimer's disease is modifiable, which means, or environmental, which means that it's education, vascular aspect, social deprivation, it's all included into this modifiable sector. Now, if we concentrate on genetics only, I would obviously we might have specialists from different fields. So we have more than less percent heritability accounting for early onset, family mutations, rare mutations, etc. But that's really only more than 1%. ApoE4, that's another quite interesting gene for Alzheimer's disease. It's a relatively common gene. So minor allele frequency of E4 allele, which is a risk allele for Alzheimer's disease, is about 14%. And the effect size of relatively common allele is quite strong. So odds ratio is about 3.2 from different studies. And if we look at the ApoE region, because it's quite a large region of LD spanning about 2 megabases, and there are some signals which are partially independent from ApoE. So there are debates, is it exactly ApoE gene or any other genes in that region? So that region accounts for about 5 to 9% of heritability. Next, we know that there are a number of genome-wide significant loss have been identified, and it's now about 40. A new paper just appeared on bioarchives and submitted into the Nature Genetics suggests another about 10 losses, so about maybe 50 at the moment, slightly more. And we know that heritability, they contribute about 3 to 8% heritability. Not new, but those which were up to 40, that's what these estimates are based upon. We also know that there are other SNPs which contribute into heritability, which estimate SNP-based heritability or narrow sense heritability is estimated between 24 and 53%. So there is a chunk of SNPs here which contributed to the heritability, SNP-based heritability. However, they are not accounted, obviously, not by the strongest ApoE, strongest genetic risk, ApoE4 or genome-wide significant SNPs. So we do have some extra information in the genome. And also we know that about 14% it's other genetic variation, which contributes to the overall genetic, to the overall broad sense heritability, which is not, we believe that it's not, hasn't been found yet. So that is rare variants, which we don't cover very well with imputation. So sequencing studies might help here. It is genetic interactions, epistatic effects, etc. Because so far, SNP-based heritability, obviously, it's additive effect of SNPs, but not interactive effects of them, non-linear effects. Yes, and of course, with the development of genome-wide association studies, you can see that we started in 2009, and that is our study, and our sample was about 10,000 individuals, total cases uncontrolled. In 2019, we have already about 100,000 individuals, fantastic, 10 times more, and also we have many more genes, and that's a publication of Kunkel et al. There are a few more genome-wide association studies after that publication, but it's the last, and that's what I used for the numbers, and which you see in this presentation, because the summary statistics was publicly available, number one, and number two, cases and controls were, well, cases were clinically assessed, and controls were either matched elderly controls or population-based controls. Latest studies are including like Janssen et al. And Marioni et al. They include UK Biobank data, where the AD cases were kind of analyzed, and they were proxy AD cases, which means that only we know from report of the participants that their parents had any type of dementia. And therefore, we use kind of clinical diagnosis here for generation polygenic risk scores, etc., rather than this AD genome-wide association study via proxy. So let's come back a little bit. So why would we consider signals which are not genome-wide significant, but other? So this is two tables which we published in supplemental material in 2015, looking at intervals of significance for SNPs, number of SNPs which contribute or which sit in this interval. We also estimate that number of independent SNPs, accounted for OD. So out of, for example, 1,200 SNPs, actual SNPs, only 737 were kind of independent. And then we looked at the expected number of SNPs being significant at that particular level, expected number of independent SNPs and actual number of independent SNPs, and calculated ratio and obviously significance. If it's significantly more than we'd observed by chance. Obviously, on a very highly significant level, we observed many more SNPs, significant SNPs that you would observe by chance. And if you look here, up to whatever 0.05, we see enrichment and significant enrichment of SNPs which are not genome-wide significant, not even nominally significant, but still contributing to the signal. And similar, we've done excluding genome-wide association loci, ApoE excluded as well. So obviously then we see less SNPs significant on this significance level, but however the ratio still remains being significantly enriched for signals or SNPs which are not even nominally associated. That tells us that perhaps a polygenic risk score might be of interest. Before I move to the polygenic risk score and estimates and precision accuracy by polygenic risk score, what we also have done, looking at heritability estimates with all SNPs, with ApoE region and genome-wide significant associated loci. Yes, 0.24. You've seen it in my first slide with the circles. For all SNPs in the genome, 5% I used here for ApoE region, and it's 55.2% when included genome-wide associated loci. What we can do, assuming that we have like 2% live prevalence of the disease in the population, right? We can estimate, using mathematical approaches, estimate the maximum prediction accuracy which can be achieved with this live prevalence and with this heritability estimates. So maximally, theoretically, we can achieve up to 82% accuracy, or measured as area under the curve, if we use all SNPs in the genome. Looking at ApoE region only, we can, and with this heritability estimate, we can reach 65% accuracy, theoretically, and including genome-wide associated loci, 66% accuracy, theoretically. Looking at different disease prevalences, because obviously Alzheimer's disease is age-related, and therefore the older you are, the higher the prevalence of the disease in that particular age group. Let's say 17% prevalence in the age group 75 to 84 years old, and you can see that prediction accuracy in that group can increase up to 84%. And basically, we calculated for a higher prevalences as well. So that was nice to know. So theoretically, we can achieve that, given that estimates of the heritability are correct, well, approximately at least. We looked at actual data and what actual accuracy we can achieve. So we looked at our first study, 3,000 AD clinically assessed cases, and 1,500 elderly age-matched controls. And we checked a number of models here. We looked at number of SNPs and at accuracy, which we achieved predicting the case control status in our data set. Obviously, to calculate polygenic risk score, one needs to have effect sizes of SNPs estimated from elsewhere, and this elsewhere is a summary statistics based upon samples not overlapping with our cases and controls. So what we used here for these estimates, at that time it was Lambert et al. Summary statistics for Alzheimer's disease. Our data set, including this one, was part of it, of the publicly available one. However, for this analysis, we asked and excluded our sample from the total summary statistics, and that's what was used to estimate effect sizes and SNP selection from this genome-wide summary statistics. So it was summary statistics, was independent samples from those which we used for testing. Right. And now we're testing model for E4 allele only, just one variable number of E4 alleles, obviously one SNP, and accuracy about 67%. So remember in the previous slide, I have said that with ApoE region, we can come up to, well, 65% accuracy. So we are slightly better here. And I think that's simply because we knew exactly a number of E4 alleles for these people. So, and the accuracy is about 68%. If we add E2 allele, it's also allele E2, it's a SNP which is protective for Alzheimer's disease. So if we add and look at the prediction accuracy, it's slightly better. So when we included at that time, it was 20 genome-wide significant SNPs. We increased accuracy up to 72%. And then as we started adding more and more SNPs, up to 0.5, not significant nominally, but 0.5 significance level, we observed increase in accuracy up to 74.5%. Yes, a theoretical one, if you remember from a previous slide, was 82, and the data is noisy. That data was not imputed early days. We achieved about 75% accuracy, which is great. Also, if we add age and sex into the model, we achieved up 78% accuracy, which is, well, reasonably good. Also, we looked if including extra SNPs and the polygenic component improves the model fit over ApoE. And ApoE here I used 2 SNPs, right? So, and it did improve indeed, up to again 0.5, and then it's basically stabilized. It did not increase any better. So that was our first publication demonstrating that polygenic risk score could be useful for prediction case control status for Alzheimer's disease studies. So let's introduce polygenic risk score formally. So that's a polygenic risk score for a particular individual I. It's a sum across the whole genome, M capital SNPs, with effect sizes taken from the GWAS, independent from testing sample, and the number of risk alleles. So basically, it summarizes information from all risk alleles in the whichever you have chosen. In this case, was from the whole genome, independent, so they need to be LD prone and added together. So just to not to be too optimistic, so what we want to have, we want to have 2 normal distributions of polygenic risk which are distinct, and then we would be fantastically discriminating cases and controls. So since we are accumulating a number of small effects, large number of small effects, polygenic risk score from central limit theorem will look as normal, and that's exactly what we observe in our data. But in reality, these 2 distributions of cases and controls actually overlap a lot. And that picture is in practice. What I said, that's what we've seen in the sample, in our sample of cases and controls. So the publication which you've seen in the previous slide. So they are separating. So in psychiatric genetics, they're more like this, but in Alzheimer's disease, at least in our samples, they were separating quite well. That's real data. So white here are controls shifted to the left, as you expect, as one would expect, and gray here are cases shifted to the right. So polygenic risk score here is standardized. So this is why the values are between -4 and 4. Also, you can see that this distribution is slightly, we have this slightly, well, bimodal, if you like, and that is ApoE4 because it has such a strong effect. So you have this not perfect distributions because that is theoretical, but slightly having some bumps. So that's a practical example. Right, so the next question is, what is our disease model? Because obviously this result was, people were trying to replicate it. So polygenic effect, which includes here genome-wide significant SNPs up to 0.05, which we reported originally. And some other studies started reporting that they can't see exactly the same pattern. They can see oligogenic model, so only genome-wide significant SNPs, or only SNPs with p-value, say 10 to minus 5 contribute to the disease, and that's what they could see. So what does it mean looking at this table? So oligogenic model would include small number of SNPs, well, 130, it was in my study 10 to minus 4, or polygenic model, which includes hundreds of thousands of SNPs. 87,000 was in this case, in my previous example. So, and why that happens? So what exactly is a disease model? Of course, nobody can answer this question for sure. So we only can publish what we see in our data. However, I think that the problem is that ApoE is not only a high risk factor for the disease, but it's also a modifier. What it means that it also modifies age at onset. For example, in this publication, you can see that if people are E4 and homozygous for E4, 91% of them will have mean age of onset at 68 years. However, if you don't have E4 allele, so you're not non-carrier, however, you still can develop Alzheimer's disease, and that will be much later, in age 84. Also, another complexity here is that this frequency, that graph shows frequency of ApoE4, E3, and E2 alleles. The frequency of ApoE4 alleles goes down with age. And why? It's simply because this ApoE4 allele is not only a risk factor for Alzheimer's disease, and once people get Alzheimer's disease earlier than others, they in average die within 7 years after. So we reduce number of people in the population with E4 allele, but also these people develop cardiovascular problems, diabetes. There was a number of other diseases associated with E4 allele, which also make people to die earlier. And therefore, prevalence of the disease increases with age, but ApoE allele frequency decreases with age, which is the strongest risk factor. And when we account for that, that's exactly pattern what we observe. So again, that is our sample. Now, not the same which we published originally, a different one, 300 cases, about 300 controls. This sample was not part of the summary stats, which we used for polygenic risk score. And looking at allele frequencies in the whole sample, indeed the same picture as reported previously. So the E2 allele frequency pretty much remains the same. E4 allele frequencies goes down, and E3 allele frequencies goes up with age. So exactly the same as we've seen in the previous slide. Now, when we look at cases and controls separately, right? So that is, again, E4 frequency goes down quicker in cases than in controls. Again, makes sense. And these two lines are oligogenic score, those which is based on a genome-wide 10 to minus 5 are included, 66 SNPs with p-values 10 to minus 5 and below, and polygenic risk score, which includes about 68,000 SNPs with p-values 0.1. Now, I'm including 0.1 because now this analysis is based on CANCO, so latest clinical data, case control data set, right? So we slightly reduced because the effect size is better estimated, so we slightly reduced the p-value threshold for inclusion, but because we cover more SNPs with modern genotyping platforms and modern imputation, so we remain approximately the same, 78,000 SNPs. So what happens? So oligogenic score, so genome-wide significant signals and highly significant ones also reduces with age, but polygenic risk score increases with age. And it's absolutely opposite picture when we looked in controls. So, and that's what increasing polygenic risk score with age, and that's age a component which needs to be taken into account. So how do we do that? So again, the same sample, and that is area under the curve, or R squared if you like, whichever measure you prefer to assess the predictability, when PRS is generated as one score. So ApoE is basically one of those 80,000 SNPs, and basically that's standard software will do that for you. And indeed, ApoE alone, 70% accuracy. When we start adding SNPs just as one score using, we go up to 65%, actually drops, as other people observe. When we look at PRS without ApoE region, which is spanning 2 megabases around ApoE gene, actually accuracy drops, of course, because it's high risk factor, but increases if we include SNPs with up to 0.1 p-value threshold. And now, that's model which I used in my original publication. Now, when we use polygenic risk score without ApoE, and ApoE variable as an extra one, extra term 2 variables instead of just one, we observe exactly the same pattern which I've seen before. So basically, this is how you need to model polygenic risk, if you like, with care, and looking at these special genes and as ApoE separately, and think if they are also disease modifiers, not just disease risk, increasing the risk for the disease. Okay, so that is done. These models, we know what's happening. We think we know. Methodologies. There are so many methods to calculate polygenic risk score. So pruning and thresholding, it's the simplest one, and that's which I was talking about so far. Precise software which uses this approach basically make it automatic choice for you, but that is a danger. If you use just a standard software, it will generate one score from all SNPs, not looking at special effects like ApoE. Polaris is a software which it's my group which we did, and we are adjusting for LD, using all SNPs, adjusting for LD mathematically. And there are a number of Bayesian approaches which introduce prior distribution or prior knowledge into before you select SNPs for calculating polygenic risk scores. Some of these approaches don't do any pruning, so you can use all SNP, just downweight the effect sizes if you think that biologically that's LD functional, or in terms of heritability, they are not picking up much information. So you just reduce a contribution or reduce beta coefficients when we generate polygenic risk score. So what we observe, that's our results, just to compare methodologies. So we have oligogenic score, let's say area under the curve for R squared, whatever you prefer to look at. So it's when you look at pruning and thresholding, it's about 72%, and they're pretty much the same, apart from perhaps as Bayer's R method, which is slightly smaller. But again, if you look at polygenic risk score, here we have 3 bars instead of 2. So full PRS when we use it as one score, and indeed it's slightly smaller than oligogenic score, and you know why. When we remove ApoE, obviously the accuracy drops, but when we include it as 2 variables, that's the best accuracy which we can achieve. And again, as you can see, all methodologies based on polygenic risk score modeling ApoE separately, they do pretty much the same, slightly better, 1 or 2%. So the conclusion was good, we can use any methodology, but if we use different methodology, do we find the same individuals? So at least ranking of individuals remains the same. And the answer is not really. So what we looked here in this picture, we looked at the extremes of the distribution. We thought perhaps people which were high risk for Alzheimer's disease or very low risk for Alzheimer's disease, because perhaps with different methodologies, these are the same. And even that's not the case. So here we looked at cases and controls and identified with different methodologies. You see they are here in the box. So the best concordance is between pruning and thresholding, precise, LD-PRET infinitesimal, PRSCS. So you see the most number of people with sick lines are the same, but some methods give you very different people, even at the extremes of the distribution. So if you ask me as a statistician, so what should we do? Which method should we use? The answer is, well, perhaps one of those which is corresponding best between each other, or those which is most understandable to you and which corresponds to the purpose of your study. And I will touch upon this in a bit later. And here just to show that polygenic and oligogenic model, and for E33 individuals which don't contain this risk effect, high risk allele, so polygenic model have odds ratio 95, looking at extremes, which is very high, of course, very broad confidence intervals, and the oligogenic model doesn't pick up them at all. So, I mean, basically, we believe that there is a polygenic component, and for example, people without strong risk, they still can be identified with a polygenic risk score, but not with an oligogenic one. Now, next step is how to include rare variants. So I will not talk too much because I know that my time is close to an end. So what we think, with rare variants, it's tricky. So that's, again, that's a polygenic risk score. Now we're looking at the probability of a disease, right, based upon polygenic risk score. And here it is in general population. So the higher polygenic risk, the higher is probability. But if you look at general population, it's not that high. If you look at the group which is 85 plus, obviously, the probability is quite high if your polygenic risk score is high. If you happen to have a rare mutation, which is APP, which is really a familial mutation, you will have probability during your lifestyle high, no matter what is the polygenic risk score, and even higher if one managed to live till 85. So that makes sense. And similar methodology, we have formulas, mathematical formulas can be used for other rare variants with strong effects, and this is an example for TREM2. I will very shortly stop on the pathways, will not show you much results, but one of other approaches to increase perhaps predictability by polygenic risk score, make pathway-specific polygenic risk score. Perhaps they predict subsets of your data better than just cases and controls. So it was a number of pathways identified for polygenic for Alzheimer's disease. They're mostly lipid-related. Here they are, lipid-related, cholesterol transport, activation of immune response. And we looked at their predictability. They are significant, distributing cases and controls. These are the p-values. Some of them are significant over and above ApoE, but not so. And if you try to distinguish amyloid positive versus amyloid negative, we'll also see a signal, but not as strong and not as predictive. So that is our conclusion about pathways so far. But obviously, we need to predict not perhaps cases and controls. We need to look at particular specific disease subphenotypes rather than just a very rough case control status. Okay, in conclusion, so it's expectation that in Alzheimer's disease, like in cancer, for example, a comprehensive genomic profiling can be critical to either choose people for targeted therapies or interventions. There are no there is no cure yet, of course. However, as I said, we should be really very careful what we try to use polygenic risk for. So if it's just exploring disease mechanisms, it's one way to do them. You can do them functionally, using functional SNPs, pathways, etc. Or if you look at the particular individual risk. And at the moment, we believe that the accuracy is not fantastic to use in clinic because, well, 75% in our cohorts. And of course, one should really take care how we deliver polygenic risks to the population. And I think we'll have a discussion later on that. And finally, my team and funders, and thank you for listening, and I'm happy to take questions.
Thank you very much. That was a great start to the workshop. Great talk. Thank you very much. You covered a lot of ground there. So just to remind people, please put any questions you have in the chat. We've already got one, but maybe I can start off. Can you just comment on ethnicity and what you've done for Alzheimer's disease, and presumably that's mostly from a Northern European ancestry population?
That's right. So far, yes, we've done it for European ancestry because the genome-wide association studies are available and they are robust and they are large. We are waiting and waiting for population ones. I know that there are a couple of in Chinese studies, but they are quite small. They are even not replicating as well ApoE4, strongest risk in European populations. They do show some significance, but not as strong. So definitely European GWASs will not be suitable for ancestry-based GWASs, no.
Okay. Okay, there's a question on the chat. Maybe you can see it. It's from Chakradara, who is at the University of Geneva, I think. It says, for time-dependent outcome of cumulative incidence, whether ROC curve and AUC is the ideal way of testing sensitivity and specificity for prediction.
No, but that is most acceptable one, mostly used and mostly reported, so we can compare between studies. Perhaps, of course, when you want to go for predicting cases only or controls only, you can go for these sensitivity and specificity measures. That's what I would answer as a statistician, but not as a clinician, perhaps.
Okay. Great. I've got another one from Catherine Lewis. Presents some results with age and sex in this model, others without. What is your opinion about whether or we should include these variables in PRS models?
Yes, so the first one was without and with age and sex. And now what we're trying to do, I think, again, with sex, we are not sure if it's actually very different. Some papers are saying that there is different in male and female. Some earlier studies show it's not. In any case, it's not strong effect of sex. I mean, when you add it as a variable, at least in our data sets, that's number one. With age we need to take carefully. And as I have shown for ApoE effect, for example, yes, we should take it into account for sure, but I think we should either model the disease in different age groups, and that's probably the best way forward, because age is it's a real problem to model age-related diseases, complex diseases.
So there's two other questions, short and hopefully short answers you can give. Would PRS be informative with progression of disease, MCI to AD, for example?
Yes, yes. So we did, again, in a relatively small sample, we tried to look at going from MCI to AD. Yes, PRS was predictive, not as predictive as between cases and controls. What we also noticed that ApoE is predictive for amyloid, so amyloid positive, negative, and those people which are amyloid positive, not all of them will develop Alzheimer's disease, and PRS is predictive who will, well, statistically significant, who will who will go to develop disease and who will remain with MCI, for example. That's, yes, but we need to look into that, of course.
Okay, and a last question before we move on to the next speaker. A direct consumer test using AD SNP scores, and what's your opinion of these?
Well, yes, interpretation of that might not be the same. And again, the devil is in the details. You know, we need to know exactly how it's done. And I don't think it's very precise. Sorry to say so.
Okay, Valentina, thank you very much. There will be other questions that come through, and maybe you can answer them on the chat if that's okay. So, continue the dialogue.